In this video I will explain why a solar eclipse can begin and end at sunrise, or why a solar eclipse can begin and end at sunset. For this purpose, I use my solar eclipse program FInspektor. This Windows program can be downloaded for free from my webpage robertneuffer.ch. With this program you can visualize the progress of any solar eclipse between the years -4999 and +7000. Solar eclipses are selected by entering the desired year into the year field. The program shows then the first eclipse in this year. Jump to the next eclipse by clicking the forward button of the scroll bar on the right. Alternatively you can enter a Saros number. Then the program jumps to the first eclipse of the Saros series. Jump to the next eclipse within the Saros series by clicking the +1s button on the right. FInspektor shows the orthographic view of the Earth as seen from the Sun's direction. The x-axis of the image is not the ecliptic. The image is always tilted into the Besselian reference frame. In this system the polar axis of the Earth looks vertical. The North Pole points toward the Sun during the northern summer half-year, and the South Pole points toward the Sun during the winter half-year. In this orientation all places along the left horizon experience sunrise, where all places along the right horizon experience sunset. You can zoom using the mouse wheel. You can move the Earth over the screen by dragging using the left mouse button, and you can reset the view by right-clicking and pressing the Reset View button. To make you familiar with the general progress of a solar eclipse, I choose the total solar eclipse of July 22, 2009. Moving the position of the scroll bar below the image, you can follow the eclipse over a time span of 3.5 hours around maximum eclipse. The partial eclipse begins here on the left, thus on the morning side. Typically this point is named P1. As the eclipse progresses, there are 2 points on the left horizon experiencing begin of partial eclipse at sunrise. Later, totality begins at sunrise. This happens approximately here. Then, central eclipse occurs at sunrise. The program shows some parameters of the now starting center line. Some minutes later, southern zero magnitude maximum eclipse occurs at this point. This is the southern extreme point of the partial eclipse on the sunrise side. I call this point PS1. Later on, we have another zero magnitude maximum eclipse at this point here. This is the northern extreme point of the partial eclipse on the sunrise side. I call this point PN1. In the further progress of the eclipse, the partial eclipse ends at sunrise for all places on the left side on the penumbral shadow cone limit. Finally, the whole lunar shadow is on the Earth's surface. Typically, this point is called P2. From now on, the complete lunar shadow sweeps over the Earth. Maximum eclipse with maximum duration of totality is approximately here. Hours later, the same can be seen in reverse order on the right, thus on the sunset side of the Earth. The outermost edge of the penumbral shadow leaves the Earth at point P3, somewhere here. There we have the begin of partial eclipse at sunset. After P3 there are 2 points along the right horizon experiencing begin of partial eclipse at sunset. Later, northern zero magnitude maximum eclipse occurs at this point here. I call this point PN4. Then, this is the southern extreme point of the partial eclipse on the sunset side. I call this point PS4. Finally the eclipse ends at sunset somewhere here. This point is usually called P4, and the eclipse is over. The total solar eclipse of July 22, 2009 was a typical example for a solar eclipse where the minimum distance of the shadow axis to the center of the Earth was small. In our common notation, the value of gamma is only 0.069. The unit of gamma is equatorial Earth radii. Let's now switch to one of the eclipses in question, the total solar eclipse of March 30, 2033. Gamma is nearly 1, namely 0.978. As seen from the Sun's direction, the central line of this eclipse is very tangential to the Earth. We can see that the yellow central line lies completely on the left side of the polar axis, thus on the sunrise or morning side. I center the globe, and I go back in time 3.5 hours before eclipse maximum. At this moment, the eclipse has not yet begun. Please look what happens to the Earth in the next 7 hours. To do so, I use the time slider on the lower edge of the program form. We can go forward and backward in time, as we want. The partial eclipse begins at sunrise approximately here, which is northeast of the Hawaiian Islands. For a better view of what's happening in the more interesting regions, I zoom in. The total eclipse begins at sunrise approximately here. The outer edge of the umbral cone touches the Earth's surface and the horizon. The central eclipse starts at this point, of course on the sunrise side of the Earth. About 6 minutes later, the complete umbral shadow is on the Earth. For eclipses that are even more tangential than this one, it is possible that not the complete umbral shadow touches the Earth. And even the central line may lie outside the Earth. These eclipses are then called non-central ones. Following the progress of this eclipse, maximum eclipse occurs at 18:01 and 18 seconds with the Sun only 11 degrees above the horizon. The central eclipse ends approximately here in the horizon, left of the North Pole, thus again on the sunrise side. If we look at the situation of the center line, but much later, we see the typical C-shaped center line for such eclipses. For eclipses beginning and ending at sunrise, it is a mirrored C. For eclipses beginning and ending at sunset, it looks indeed like the character C. A prominent example for a C-shaped eclipse path occurred October 3, 1986. This very interesting eclipse was discussed extensively on the Solar Eclipse Mailing List. In addition to the C-shaped center line, the eclipse was neither total nor annular at eclipse maximum. Because the Moon is not a perfectly polished sphere, there is no instantaneous transition between annularity and totality. There are high mountains and deep valleys on the rough lunar surface. At the theoretical moment of the transition from annular to total, sunlight shines through valleys along the lunar circumference. To eclipse observers this effect is known as Baily's beads. Another C-shaped total solar eclipse will occur on August 23, 2044, as was discussed on the Solar Eclipse Mailing List. Playing with the FInspektor program, you will now understand why or how totality begins and ends at sunset, in this case. I hope you enjoyed this video.